We do it every day. We know the sun will rise and what direction it'll rise from. We know that if something is thrown, it'll eventually land, and that creating a fire will produce heat. Of course, these are easier predictions to make, because we've experienced them happening many times, and consistent trends are safe bets. However, we can increase our prediction making power by knowing why they happen. This is more important because that way we can make adjustments to our predictions based on changes in the environment. For example, the sun rises and sets differently depending on what time of year it is and how close you are to the poles. Sometimes the sun never sets or never rises because of the relationship between the tilt of the Earth and the sun. Also, if you throw something in space, it won't land the same way it would on the ground because gravity is weaker. Many of the predictions we want to make have much greater detail than these. Meteorology, for example, is concerned with studying and predicting weather. It involves details like wind speed, atmospheric pressure, humidity, where large masses of hot and cold air are, etc. In short, numerous factors influence the weather, and the ways they do so require complicated equations to describe them. Now here's the question. Just how precise can a prediction be? At the lowest level of reality are particles, quarks, electrons, photons, and a few others. These particles interact with each other and influence each other's movement just as anything else does. So it's reasonable to assume that if we knew exactly where they all were and where they were going, as well as the rules for how they interact with each other, we could perfectly predict how a system of particles would change over time. So, could we do this to the whole universe? Could we simulate the universe and be able to perfectly predict all future events? There's a couple major barriers to this. The first is a pretty big one that gets a lot of attention: quantum physics. This big bad field of weird physics stuff that deals with a lot of probabilities and not a lot of certainties. Here's the really basic reason why this is the case. Let me preface this section by saying that quantum mechanics is complicated for even the experts. I've done my best to produce an easy to understand description of why things be, but I can't guarantee I'm absolutely correct about it all. It should, however, be close enough for the purposes of this topic. We used to think particles were like little balls, having a certain position in space and a certain speed in a certain direction. This would make things easier. However, we found out that they also act like waves. That is, they have a property that makes it so their position and speed aren't certain at all times. This property is called a wave equation, which is actually exhibited by anything that acts like a wave, such as the ocean. On the quantum level, these particles' wave equation is described by the Schrödinger equation. Basically, this can tell us how various properties of a particle, such as its position, changes over time. However, because it results in more than one value, it actually gives us a probability that such properties will be any one value at any point in time. That being said, when a particle interacts with something, they have to possess certain values. So we say at this point that the wave function collapses. Let's set up the experiment. We release a particle into a vacuum chamber. It's pretty much all by itself, meandering through the room. Now we send out some photons, one at a time, until one comes back, showing that we've observed the particle somewhere. Based on the properties of the returned photon, we can infer some information about the particle we're trying to measure. These properties include the position and the speed. Are these the right values? Maybe. Let's send out some more photons. Now we have a bunch of different results on a timeline. It turns out that these results are kind of hard to predict. No matter what model we use, it's always off by a little bit. We can tweak the experiment to get more info on either position or speed, but this always results in the other getting harder to predict. Here's what's going on. The wave function of the particle is made up of a bunch of different waves, each one representing a different property. Position and speed in particular are represented by waves that are mathematically perpendicular to each other. Because of how the math of these waves work, we can squeeze them to get more precise measurements, but this results in the other wave stretching out, becoming less precise. This is what Heisenberg's uncertainty principle is. Truth is, it took me some time to understand why it was different from what I'd been told. Probably because it's more complicated unless you know how statistics works. Take a look at it. Delta p times delta x is greater than or equal to h over 4 pi. The delta p and delta x represent what are known as the standard deviations of position and speed. When we get our set of data, the standard deviation is how much, on average, any data point differs from the average. Basically, you can get more and more precise measurements by making that deviation smaller, meaning that every data point will be closer to the average, but the result for the other measurement is the deviations will get bigger, making it less precise, and the data strays more from the average. Also, that h is the Planck's constant. For now, just know that number is very, very small. So the important bit is that the product of the two deviations is never zero. It can just get pretty damn close. Earlier I said that when the wave function collapses, the properties of the particle are forced to a certain value. It turns out that for some special values, which include position and momentum, this doesn't occur. Instead, they turn into a set of values that are close to each other. If you want to know exactly what makes them special, Wikipedia says they're continuous spectrum operators, and that these are non-normalizable. There's something to Google. I feel like that's probably beyond the scope of this video. Now, if we didn't care about being absolutely precise, we wouldn't have to worry because the seeming randomness averages out to no effect on a macroscopic level. If you fire a baseball under the same conditions 100 times, it'll land in basically the same spot every time. It might change by a few atoms worth of distance, but nothing that would drastically affect the future. There are a few very specific circumstances where quantum probabilities can cause macroscopic effects, such as superfluids and superconductors. Superfluids have zero viscosity, so they can do things like create eternal whirlpools. Superconductors work similarly, having an electrical resistance of zero. This is similar to friction, so electricity fed into a superconductor loop can flow forever. These work because the materials have been supercooled. Classical mechanical effects like heat end up becoming a dominating influence on the behavior of systems when there's a lot of particles at play. So taking away that heat and nullifying any classical mechanics influences means that the particles can now show off their quantum weirdness. Now let's assume that somehow we do have all the information we need, the location and the speed of every particle in the universe. No vagueness or probabilistic weirdness. Calculations ready to go. Except no, because there's one more problem. Gödel's incompleteness theorem. This is a pretty significant math concept that says, for any system of axioms that's consistent and complete, there are statements about it that can't be proven or disproven by that system. Let's walk through Gödel's theorem now. First, a system of axioms is pretty much just a list of statements, but to be complete, all these statements need to be provably true or false. Now, such a system is consistent if it doesn't have any contradictions. That means no statements can be both provably true and false. The theorem states that no system of axioms can prove itself to be consistent, so there will necessarily be at least one statement that will end up being both true and false. Furthermore, the theorem states that if such a system were consistent, then at least one statement would be unprovable. Let's try to illustrate this in a basic way. To start, let's say every single math and logic statement has a unique number that can be applied to it. This means stuff like 2 equals 2, 3 plus 1 equals 4, 5 times 3 equals 15, and 1 and 0 equals 0. All have a unique number on the list of all possible statements. These unique numbers are known as Gödel numbers. There's a specific method for working out these numbers, but that's not important here. I'm going to refer to them from now on as IDs. Now let's say we can also apply IDs to statements about statements. For example, the statement 4 is the last number of the statement 2 plus 2 equals 4, also has its own ID. Now here comes the hard part. We can also describe statements defined by alterations of other statements. These statements are structured like this. Now here comes the hard part. We can also describe statements defined by alterations of other statements. These statements are structured like this. You have sub x, y, z. The x refers to the ID of the statement we want to alter. The y refers to the symbol we want to swap into the statement. The z refers to the ID of the symbol we're swapping out. So if you gave 2 plus 2 equals 4, the ID 4, and the number 2, the ID 2, then you wrote sub 432, that would mean you're taking 2 plus 2 equals 4, swapping out the 2's, and replacing them with 3's, creating 3 plus 3 equals 4. These two statements, sub 432 and 3 plus 3 equals 4, would then have the same ID, since they result in the same statement. Now then, let's say we have some statement. Its ID is x. Now let's create the statement sub xx2, give it the ID y. This says, for the statement of ID x, replace all the symbols where the ID equals 2 with x's. For this example, we're saying that the ID of x is in fact 2, although in the actual system of IDs this is not the case. Now we have a couple more steps to go. First, we make the statement sub yy2. This says that we take the statement of ID y and replace all the symbols of ID 2, the x's, with a y. Here's the important question. What's the ID for sub yy2? We could just assign another variable to it and call it a day, but it turns out that structuring a statement like this produces an interesting result. If we follow the instructions and replace all the x's in the statement of ID y, which is sub xx2, with y's, we get sub yy2. Ultimately, we're right back where we started. Because of the specific method for how IDs are calculated, the ID for sub yy2 ends up being the statement itself. Bear in mind that for this to work, it shouldn't be attached to the original statement 2 plus 2 equals 4, but rather any statement we decide to ascribe the ID of x to. That is, this logic holds true for any and all statements. Finally, let's say that instead of the statement simply being sub yy2, it was, instead, the formula with the ID of sub yy2 isn't provable. Because the statement refers to itself, we've created a paradox of self-referencing, just like the famous "this statement is true" paradox. If the statement itself claims it's unprovable, we end up with an undecidable statement. However, this does still mean that it's unprovable, and so we end up with a proof of an incomplete system, since we have a statement that is not decidably true or false. To give you an example of how this practically affects us, let's take the computer you're using to calculate the future. That computer is made up of particles that exist in the universe. Is it going to take itself into account? That's going to be kind of hard, since every move it makes affects its own calculations. The transistors you're using to calculate the universe can't reference themselves. The only way to escape this would be to put the computer outside of the universe, so it can't affect the system it's trying to completely prove. It is also worth noting that this does create a new system, Universe Plus Computer, that does possess another such undecidable statement. So that hasn't completely gone away, but since we only care about proving a subset of that system, we should be fine.